my name is Elizabeth, and welcome to my presentation, Exploring the Effectiveness of Using Large Language Models to Detect Cryptographic API Misuse. Cryptographic APIs are software packages that allow developers to easily access cryptographic algorithms to help them implement secure coding practices. And while many developers use cryptographic APIs to secure their code, they do not necessarily understand the details behind these APIs and subsequently incorrectly implement cryptographic rules in their code, leading to cryptographic API misuse and vulnerable code. Cryptographic API misuse is a widespread problem that can leave systems vulnerable to attacks. Thus, being able to successfully detect cryptographic API misuse in code is very important for developers. This widespread problem stems from the fact that some organizations do not prioritize security or do not have the resources to bridge the gap in security knowledge within their developers. Hiring security experts is simply not an option for some, as it's expensive and can lengthen the time it takes to complete projects. However, keeping up to date and properly implemented security in systems is incredibly important, and so we need a solution. And this is where static analysis tools come into play. Static analysis tools, up until recently, were considered the most affordable and effective way to identify vulnerabilities in code during software development. And while they still are widely used and helpful tools, specifically within the domain of cryptography, static analysis tools have been known to provide many false positive and false negative results, which is not ideal as it leaves vulnerabilities, specifically cryptographic API misuses, open. The introduction of AI in the past few years has developers frequently turning to LLMs, such as GPT models, for coding assistance and queries. This transition has inspired questions about the effectiveness of AI in detecting software vulnerabilities, such as cryptographic API misuse, especially in comparison to current static analysis tools. As developers use LLMs more for coding help, it is imperative to study how effective these models are at answering queries about software vulnerabilities. LLMs are known for having the possibility of giving misinformed and variable responses, thus many of the studies about the usage of LLMs also explore how developers can better interact with the LLM to get a more reliable answer. And this leads to the field of prompt engineering, which I will get deeper into later. Most of the current research in this field has been centered around Java and its benchmarks and cryptographic libraries. However, there are a few that start researching the Python language. Python is one of the most popular languages these days and has extensive cryptographic libraries, so it's crucial to research the extent to which GPT models can be relied on to help detect cryptographic API misuse in Python. Many studies on cryptographic API misuse focus on intra-procedural and inter-procedural test cases, and their measured results are from studying the combinations of both kinds of tests. However, my study will focus only on inter-procedural test cases, meaning we will study how well tools can detect cryptographic API misuse that spans multiple functions within one file. This can be calling a function within a function, passing in parts of a command as an argument from a different function, and much more. Overall, these test cases challenge if a tool can detect cryptographic misuse patterns that require analysis of interaction between different functions. For example, these two images illustrate interprocedural test cases from the benchmark I am using in this project, which I will also cover later. As you can see on the left, from starting method, an insecure hash MD5 is passed into call method, which then uses MD5 to hash the data. And then on the right, from starting method, SSL create unverified context is passed into call method, which then uses that to bypass SSL verification. Analyzing interprocedural test cases is important, as research shows that static analysis tools are very good with intra-procedural test cases, but not as effective with interprocedural analysis, which is a gap that LLMs could fill. Through my study, I will determine if LLMs can be considered effective in analyzing interprocedural cryptographic misuse cases. In this presentation, I will study the effectiveness of LLMs in detecting interprocedural cryptographic API misuse in Python. I want to see the extent to which an LLM can become the role of a cybersecurity specialist, while still maintaining an affordability and ease of use comparable to that of static analysis tools, but with a higher accuracy of misuse detection rate. If am successful, this would mean that LLMs will be supported in being a suitable replacement for static analysis tools for detecting interprocedural cryptographic API misuse in Python. In order to evaluate the performance of the LLM in comparison to a static analysis tool, I need a robust benchmark compatible with the Python language. The benchmark I chose to use is PyCryptoBench, as this benchmark was designed specifically to evaluate the precision of tools in detecting cryptographic API misuses in Python. PyCryptoBench was introduced in the paper Methods and Benchmark for Detecting Cryptographic API Misuses in Python, which is cited on my reference slide at number 1. Developed by researchers at Virginia Tech, this benchmark comprises of 1,836 files, each containing Python test cases. PyCryptoBench spans 18 different cryptographic misuse rules using Python cryptographic libraries. I will use these 18 misuse rules PyCryptoBench is based on to determine how effective my tested tools are at detecting cryptographic API misuse in Python. These misuse rules cover things from overriding default or proper behavior to avoid verification, insecure implementation of cryptographic algorithms such as insecure random number generation, static salts, insecure encryption modes, outdated ciphers or small key sizes, insecure hashes, deprecated protocols, improper deserialization, and insecure use of regex. These misuse cases have the potential to leave systems vulnerable to different attack types comprising of SSL or TLS man-in-the-middle, predictability, ciphertext attack, brute force, and deserialization, which is why it's essential to test the effectiveness of different tools at detecting these cryptographic misuses. For my testing, I narrowed down the test cases to just the interprocedural ones, and then divided those files up into directories rule 1 through 18, depending on which misuse rule it covered. Then I filtered each test case based on if it had a vulnerability or not, which is how I identified each file as a true positive, true negative, or false negative, after using each tool to scan the files. In the end, I had 258 test files to work with. I chose to use SemGrep as the static analysis tool I would use as my baseline to compare the LLM against. SemGrep is a static analysis tool that helps developers identify vulnerabilities in their code. And the reason I chose SemGrep is that researchers who developed PyCryptoBench tested 3 well-known and trusted static analysis tools, SemGrep, Bandit, and DLint, as their baseline for comparison. They measured each tool using precision, recall, and F-score. For cybersecurity, recall's value should be prioritized in analysis, as this measures the degree to which the tool ensures that it doesn't miss any actual instances of cryptographic misuse. High recall correlates to minimizing the number of false negative cases, and for identifying security vulnerabilities, missing misuse cases can have dire consequences. Thus, from the tests the researchers who developed PyCryptoBench ran, for the interprocedural and double interprocedural test cases of PyCryptoBench, SemGrep had the highest recall scores out of SemGrep, Bandit, and DLint. Therefore, since SemGrep had the highest recall score out of the 3 tools for the interprocedural test cases in this paper, I chose to use SemGrep for my baseline analysis. I downloaded the VS Code extension of SemGrep version 1.10.3 and was able to access and run this extension in a virtual environment running WSL Ubuntu 24.04. Through this VS Code extension, I ran SemGrep on the test cases and manually went through the results, flagging them as true positive, true negative, or false negative. Now before I go into how I chose and tested the LLM, I wanted to dig deeper into prompt engineering. Prompt engineering is the process of designing effective prompts to get a more desirable response from an AI model. One of our goals is to explore how engineered prompts can increase the reliability of LLM responses. There are strategies on designing or engineering prompts to get a better response from LLM models. I will now cover some of these strategies that I implemented. The first is clarity and specificity in instructions and details. Including details about your query can lead to more relevant answers. The important thing to remember is to avoid ambiguity, as this can lead to confusion and insufficient answers. The clearer you are in your instructions and the more context you give the task at hand, the better the response will be. Part of this can be specifying constraints for the response, which gives the model a general understanding of how to structure their answer. The second strategy is asking the model to adopt a persona. You can give the model something or someone to become, such as an expert of a certain domain of knowledge, and it steers the model to understand what you need from them. Message roles is another strategy that I use. This feature is part of OpenAI's API, where you can assign roles within messages that you feed the model. I adopted the roles of developer and user. User you can think of as what you would feed the chat interface of ChatGPT. However, the developer role will contain instructions you can give the model that will be prioritized over the user messages. This will include instructions on how you want the LLM to respond, what persona they should adopt, any details relevant to the context of the user query, and any limitations to the structure of the response that the LLM should consider. This is another way of communicating to the model the needs behind your query. User intent versus model understanding is another strategy to consider. This goes along with the clarity and specificity strategy, as user intent has to be properly and specifically communicated while also taking into consideration the model's creative capabilities. While some restrictions can help the model narrow down your question's intended scope, in interacting with an LLM, it's also important to give the model the freedom to think and show off its capabilities. Another strategy is domain specificity. This means using domain-specific wording and context to guide the model towards an appropriate response. For example, since we are working in the security field for this project, we want to use terms anyone familiar with the cybersecurity field would know. This can range from types of attacks, specific vulnerabilities, and definitions. And then the last strategy I want to cover is zero-shot versus few-shot prompting. Few-shot prompting is when the developer gives the model a few examples of input and response output to show the model examples and guidance to what they are looking for. Zero-shot prompting is simply asking the query and not providing examples along with that. While there are benefits to few-shot prompting, I chose to use zero-shot prompts. I wanted to test the effectiveness of the LLM on its own training data. In a real scenario of a developer using an LLM to ask for assistance in securing their code, they will likely not have examples on hand to give the LLM. And thus, I wanted to simulate that experience and see how effective and accurate the LLM could be with a refined zero-shot prompt. For my first prompt, I used minimal prompt engineering techniques, leaving it up to just a simple query asking the LLM to do what I need, which is analyze the code for cryptographic API misuse. The instructions about the response will be consistent between all three prompts in order to automate the analysis of the responses for true positives, true negatives, and false negatives. Here I use the role user from OpenAI's API, which is equivalent to interacting with ChatGPT's chat interface. This prompt was designed to simulate how a user would interact with an LLM with minimal knowledge of prompt engineering. This will act as the baseline of all the prompts to show just how adding a few additions to this prompt can increase the accuracy and reliability of the responses. In my second prompt, I'm utilizing the roles in OpenAI's API, developer and user. In developer, I give all the necessary context and instructions that will be prioritized over the user message. I ask the GPT model to adopt a persona, as highlighted in yellow, give it a clear and concise task, which is highlighted in blue, and provide details about my specific domain, which is the definition of cryptographic API misuse and the relevant attacks we want to avoid, which is highlighted in pink. These attacks are the ones the benchmark was made specifically vulnerable towards due to the misuses in its code. In practice, we could add any attacks that we want the LLM to look out for. Beyond that, I kept the same structure of prompt 1 with the constraints for the response and the question itself. Then in my third prompt, I give the LLM the most information and context to work with. I include everything from prompts 1 and 2, the persona task and definition, but then I also add to the task by asking the LLM to look for specific cases of cryptographic API misuse, which I highlighted in yellow. And then I add the 18 misuse rules that the benchmark is based off of, highlighted in blue. I asked the LLM to look for these instances of cryptographic API misuse specifically, which I know all exist in the benchmark test files. In practice, one could compile a list of known cryptographic misuses to ask the LLM to look out for them in any given code. Now, we allow the LLM to use a set of attacks that we want to protect against, as well as vulnerabilities we want to look out for in its analysis of misuse cases. This is the highest degree of specificity we will go to in our prompt testing. I chose to use GPT-4o Mini because firstly, I could not find any studies on using this specific model to test the detection of cryptographic API misuse in Python code. The second reason is that one of the reasons behind the widespread cryptographic API misuse is the lack of resources to put towards hiring security experts to bridge the gap in developer knowledge. Not only is GPT-4o Mini cost-effective, it has strong reasoning power, as it's based off of the GPT-4 architecture. And it's advertised as a good model for smaller, straightforward tasks. And with proper prompt engineering, we can help ensure that detecting cryptographic API misuse is a simple, straightforward task for the LLM. I accessed this model through OpenAI's API through a Python script in VS Code. My script automated the counting of false positives, false negatives, and true positives, and also printed the LLM output to a file for manual analysis of the responses. Also, LLMs are known to have variable responses to the exact same prompt. So to account for this variability, I ran the script 3 times on each of the 3 prompts and averaged the results for each prompt to account for the differences in LLM responses. I will now show a demonstration. Here is how I run SumGrep using the VS Code extension. So here is the downloaded SumGrep VS Code extension. I scan all my files in the workplace. And these are the PyCryptoBench files that I'm using. So as you can see here, we get the results in the Problems tab, and also if you go into the file, you can hover over and see the misuse detected. Here I will demonstrate running prompt 1 through OpenAI's API. So here's where I access the OpenAI API, and here's my API key, and then this is the model that I accessed, GPT-4o Mini, and here is my prompt 1. And I will automatically print out my results. And here's the results. So here is the printed out evaluation summary of true positives, false negatives, true negatives, and false positives, as well as the LLM output for our test cases. Here are my results after testing each tool's effectiveness of detecting cryptographic API misuses on interprocedural test cases in Python. I measured precision, recall, F-score, and F2 score. All results had very high precision, as the number of false positives in my results was very small. However, as we discussed earlier, I will place a higher emphasis on recall over precision and F-score, as the priority from a cybersecurity standpoint would be to minimize the number of false negatives, as we don't want to miss any misuse cases. This is also why I factored in calculating the F2 score. The F2 score measures the balance between precision and recall, but with a greater emphasis placed on recall, aiming to minimize the number of positive cases that are not properly detected. As we can observe, for interprocedural test cases, SumGrep did poorly, with a recall at 27.78% and F2 score at 32.26%, illustrating its inability to effectively detect cryptographic API misuse in interprocedural test cases. The GPT model, on the other hand, did much better and improved upon using prompt engineering. For prompt 1, which had minimal prompt engineering, recall was at 69.44% and F2 at 73.75%. For prompt 2, which gave persona, task, definition, and relevant attacks to prevent, recall increased to 87.50% and F2 to 81.40%. And then finally for prompt 3, which had everything from prompt 2 and then added specific cryptographic misuse cases to look out for, recall reached 88.89% and F2 90.65%, demonstrating the potential for LLMs like GPT-4o Mini to increase the effectiveness of detecting interprocedural cryptographic API misuse cases in Python. So based on those calculations, GPT-4o Mini outperformed SumGrep on interprocedural Python test cases by a significant amount. On average, there was a percent increase in recall of 183.31% from SemGrep to GPT, and a percent increase in F2 score of 153.98% from SemGrep to GPT. Then within GPT-4o Mini itself, the recall score increased from 69.44% to 88.89%, and the F2 score increased from 73.75% to 90.65% through prompt engineering. These results illustrate how the GPT model was significantly more effective at minimizing the false negative cases than SemGrep. Both tools were very affordable, with SemGrep being free, however with lower accuracy in cases detected, and then GPT first accounting for the minimum payment of $5 to get started using the API. Then by the end of testing, I had accrued a cost of 15 cents, giving a total of $5.15 spent to test my prompts on the benchmark with promising results, highlighting the potential of this model through its accuracy and affordability. Thus, while SemGrep is free, the high recall and F2 score of GPT-4o Mini make a strong argument towards spending a little bit of money to gain better security. However, even with these results, something I would still recommend is manually reviewing the explanations of the results for both tools, as there are risks of misidentification and valuable insights one can get from the reasonings of these tools. SemGrep's detected misuses pointed out the file and line number, and the message included the detected misuse, reasoning, and solution. It linked to relevant SemGrep documentation addressing the specific rule that this code violated, and linked to external resources such as Stack Overflow or the CWE website. In the VS Code extension, it also offered a quick fix option for some of the misuse cases that fix the vulnerability identified for you. Overall, the software itself is well designed. The main pitfall is its detection accuracy. SemGrep struggled more with the interprocedural test cases as reflected in the measurements from the results. And this is because SemGrep uses static analysis techniques based off of patterns to detect misuse cases. And when part of that pattern was an argument and not directly stated, there was a higher chance it was missed by the tool. In my manual review of the detected misuse cases, I found that while some vulnerable files were properly flagged as having a misuse, the program did not always actually detect the intended misuse as defined by the benchmark's misuse rules. These files flagged some other parts of the code, and while the flag may have not been without reason, there was still an undetected misuse, and thus I labeled those files as false negatives. Another observation I had was the difference in detection between files that had identical code. I kept duplicate files in my test cases to test the consistency of detection and found that there were many cases where only 1 out of 2 identical files were properly detected as having a cryptographic API misuse. Overall, SemGrep is a well-designed tool. However, their accuracy on interprocedural test cases could use some work. The GPT model was able to analyze the context of the problem and see the relationship between multiple functions in most cases. It did not struggle as much as SemGrep did with the interprocedural structure of the test cases, nor was it as inconsistent with duplicate files. Thus, its detection rate was much higher than that of the static analysis tool. However, the LLM model does have its own things to take into consideration. While most of the files were accurately flagged, there were a few files that were not completely accurate, and I will discuss those here. Firstly, the model's analysis takes in the full context of the file it's looking at. So in a few files, in mainly the first prompt, that didn't give much detail and specifics into the task at hand, while it correctly identified the intended cryptographic misuse in the reasoning, it did not label the file as a positive misuse case, since the test code was not being used in a cryptographic context. I think this highlights the balance between providing the model guidance and limitations, and letting the model be creative in its response. The more specific we are in our prompt, the more the model understands our needs in identifying code that could be used as cryptographic misuse, even if the context of the misuse is not present in the test code. This issue, however, could be remedied by looking at real-world projects that implement cryptographic APIs, or refining the test cases to use the modules in a cryptographic manner. However, in our case, prompt engineering helped a lot. This issue decreased with prompts 2 and 3, which provided a clearer task, a definition of cryptographic API misuse to use, and samples of attacks to prevent and misuse cases to identify. With these included, the model understood to look for pieces of code that could be exploited as cryptographic misuse and lead to an attack. Second, similarly to SumGrep, in a few cases, the model correctly labeled a file as having a cryptographic API misuse, but did not correctly identify the intended misuse of that file, or only detects part of the vulnerability in its reasoning. In a few cases, in incorrectly detected files, the misuse was identified correctly, but the reasoning given was confusing or misleading, which for developers hoping to get help fixing vulnerabilities in their code could be misleading and cause more misuse cases. This highlights the importance of manual review of the model's responses, as AI is not completely perfect. Overall, GPT-4o Mini did excellent at detecting cryptographic API misuse in interprocedural Python test cases, especially with prompt engineering. By the third prompt, at least one vulnerable file in all 18 rules were properly detected, with 15 rules having all vulnerable files properly detected. Even with the impressive results the GPT model provides, there is future work that could be done to refine the reliability of using an LLM to detect cryptographic misuse cases. The first is few-shot prompting. I went over this briefly earlier, but few-shot prompting is when a user provides a few input and output examples in their prompt to guide the model's response to what the user needs. I chose not to do this as I wanted to test the extent to which a refined zero-shot prompt could provide accurate detections. However, in a case where there are relevant examples to provide the model will be able to learn from those examples and possibly provide better results aligned with the user intent. The next thing builds off of few-shot prompting, and is fine-tuning the model. This was created with the intention of providing higher quality results to the user. Fine-tuning the model improves on few-shot prompting by actually training the model on a larger set of examples, rather than just providing a few in the prompt itself. Thus, once a model is fine-tuned, the user should not have to provide more examples in their prompts and can simply query the fine-tuned model. Though it is recommended to try prompt engineering before attempting to use fine-tuning, as it takes more time and resources and requires the development of a dataset to train the model on. However, a combination of prompt engineering and fine-tuning has the potential to produce the best results. Another thing that would be interesting to analyze is testing the LLM on open-source projects. Right now, my conclusions can be extended to the interprocedural cryptographic misuse cases within the benchmark PyCrypto bench. However, this limits the scope of my results. Comparing the effectiveness of these tools on open-source Python projects could help solve this. Since the LLM automatically takes into account the context the code is in, seeing its detection ability on code using cryptographic APIs within a project that uses them for security purposes would be a helpful insight that could expand the scope of my results. Finally, this project focused on the proper detection of cryptographic API misuses in Python test cases. Something that would be interesting to explore is the effectiveness of not only the detection, but the solutions offered by each tool. SumGrep did already offer solutions and quick fixes to misuses as part of their software. The GPT model, in some cases, did offer solutions. However, since I did not specify that in my prompt and restricted their reasoning to one sentence to minimize cost and latency, most did not provide solutions to detected cryptographic misuse cases. An analysis of the accuracy of the solution offered by the LLM would be something interesting to see in future work. GPT-4o Mini provides a cost-effective way to supplement a security expert with a lessened risk of missing misuse cases than static analysis tools such as SumGrep. LLMs hold a vast potential to aid developers in writing more secure code, and with prompt engineering, the responses of these models can be refined to be even more accurate and reliable. Overall, security should be a priority, but when there is a gap in knowledge and no resources to fill it, LLMs such as GPT can come in handy. The rise in AI has led developers to more frequently turn to LLMs such as GPT models for coding help, and thus studying how to best interact with these models to receive reliable results is imperative. We set out to study the effectiveness of LLMs in detecting interprocedural cryptographic API misuse in Python, and found that OpenAI's GPT-4o Mini model provides promising results in this field. Thank you for listening to my presentation. I hope you enjoyed it.